Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the crushing darkness of the Mariana Trench, where pressure would flatten an unprotected human like an aluminum can, life has not only found a way to survive, but to thrive. The adaptations that allow organisms to endure these extreme conditions represent some of the most remarkable evolutionary innovations on our planet, turning the deep-sea environment from a biological impossibility into a unique ecological niche. The most fundamental challenge facing trench-dwelling organisms, known collectively as Hadal life from Hades, the Greek underworld, is the enormous hydrostatic pressure. At the bottom of the Challenger Deep, every square centimeter bears the weight of approximately 1,100 kilograms, equivalent to having a fully grown polar bear balanced on your thumbnail. This extreme pressure would ordinarily cause proteins to denature and cell membranes to compress beyond functionality. Hadal organisms have evolved remarkable molecular adaptations to counter these effects. Their proteins contain unique structural modifications, including more flexible bonds, additional stabilizing salt bridges, and pressure-resistant amino acid sequences that allow biological processes to continue under conditions that would render conventional proteins useless. Cell membranes incorporate specialized lipids that remain fluid rather than hardening under pressure, maintaining the cellular integrity essential for life. Among the most well-adapted creatures in this environment are the amphipods, distant relatives of common beach sandhoppers that have evolved into the scavengers of the deep. Species like Hirundellea gigas grow to remarkable sizes of up to 30 centimeters, demonstrating a phenomenon known as deep-sea gigantism. These pale, almost translucent crustaceans have developed specialized enzymes that can digest wooden debris that falls to the trench floor, breaking down one of nature's most resilient materials in an environment where food scarcity is a constant threat. Perhaps most impressive are the Hadal snailfish, particularly Pseudoliparis swirae, discovered in 2014 at depths exceeding 8,000 meters. These ghostly translucent fish contain high concentrations of a chemical called trimethylamine N-oxide, or TMAO, which prevents proteins from being crushed under pressure. Their bodies lack air bladders, which would collapse under pressure, and contain specialized skeletal structures that maintain integrity while remaining flexible enough to maneuver in the deep currents. The microbial communities of the trench present another biological frontier. In 2012, researchers discovered microbes in trench sediments living at depths of nearly 11,000 meters. These organisms not only survive, but actively metabolize available nutrients under pressures that would instantly kill surface-dwelling microbes. Some of these bacteria possess pressure-sensing genes that trigger the production of special protective compounds when environmental pressure increases. Beyond the ability to withstand pressure, trench organisms must also contend with near-freezing temperatures, scarce food resources, and the absence of sunlight for photosynthesis. Many species have developed extraordinarily slow metabolisms, essentially operating in slow motion, allowing them to survive on minimal energy inputs. Others have evolved extreme sensitivity to detect the rare food particles that drift down from above or the movement of potential prey in the darkness. These adaptations highlight nature's remarkable ingenuity in the face of environmental extremes. By studying these pressure pioneers, scientists are gaining insights not only into the limits of life on Earth, but also into fundamental questions about how life might exist on other worlds, particularly those with high-pressure environments like Jupiter's moon Europa or Saturn's Enceladus. The Mariana Trench represents far more than merely the deepest point in our oceans. It serves as a dynamic geological system that provides a rare window into Earth's interior processes. This massive submarine canyon exists as the visible manifestation of a fundamental planetary mechanism, the consumption of Earth's crust back into the mantle through the process of subduction. At this convergent boundary between the massive Pacific Plate and the smaller Philippine Sea Plate, we witness geology in action on a scale difficult to comprehend. The Pacific Plate, moving northwestward at approximately 7 centimeters per year, about the same rate human fingernails grow, dives beneath the Philippine Plate in a process that has continued for more than 180 million years. This subduction creates the distinctive arc-shaped trench that characterizes the Mariana system. The angle of subduction here is unusually steep. The Pacific plate plunges downward at nearly 90 degrees in some sections, creating one of the deepest trenches on the planet. As the descending oceanic crust reaches depths of about 100 kilometers, increasing pressure and temperature trigger partial melting. This molten material, less dense than surrounding rock, rises through the overlying plate, creating the volcanic island arc that parallels the trench approximately 200 kilometers to the west. This volcanic activity has produced the 15 islands of the Marianas, including Guam and Saipan. These volcanoes represent the most visible evidence of the powerful geological forces at work beneath the trench. Less visible but equally significant are the frequent earthquakes, some exceeding magnitude 8 on the Richter scale, that occur as enormous sections of the plates suddenly slip past one another after building tension for decades or centuries. What makes the Mariana Trench particularly significant to geologists is the access it provides to the Earth's mantle. The oceanic crust here is unusually thin, just 5 to 6 kilometers compared to the typical 7 to 10 kilometers elsewhere in the Pacific. This thinness, combined with the extreme depth of the trench, means that the Earth's mantle lies closer to the surface here than almost anywhere else on the planet. Recent scientific expeditions have recovered samples of serpentinized peridotite, altered mantle rock, from the trench walls, providing rare specimens of material from Earth's interior. The trench floor itself contains sediments that tell a complex geological story. Unlike many other deep ocean trenches that trap large amounts of sediment flowing from nearby continents, the Mariana Trench is relatively isolated from major land masses. The sediment layer here remains thin, typically less than 500 meters, consisting primarily of siliceous ooze, the accumulated shells of microscopic marine organisms, and volcanic ash from the nearby island arc. Perhaps most intriguing are the mud volcanoes discovered along the outer edge of the Mariana Forearc, the region between the trench and the volcanic islands. These unusual formations occur when fluids and gases released from the subducting plate rise through fractures in the overlying plate, carrying dissolved minerals and even microorganisms from deep within the Earth's crust. The largest of these, the conical seamount, rises more than 2,000 meters above the seafloor and serves as a literal pipeline bringing material from the deep Earth to the surface. These geological processes don't merely shape the physical landscape of the trench. They create unique chemical environments that support specialized biological communities. Through hydrothermal vents and cold seeps, the geology of the Mariana system provides energy sources for chemosynthetic organisms that form the base of food webs operating completely independently from the sun-powered ecosystems familiar to us on the surface. The waters of the Mariana Trench represent one of Earth's most chemically distinct environments, a realm where standard seawater chemistry transforms under extraordinary conditions of pressure, temperature, and geological influence. Understanding. This unique hydrochemistry has become a critical frontier in deep-sea research, revealing how chemical processes shape life's adaptations and evolution in this extreme environment. At depths approaching 11,000 meters, the immense hydrostatic pressure, exceeding 1,100 times atmospheric pressure at sea level, fundamentally alters how chemical compounds behave. Water molecules themselves pack more densely together, increasing seawater density by nearly 5% compared to the surface. This compression affects everything from the solubility of gases to the rate of chemical reactions, creating conditions unlike anywhere else in Earth's oceans. Dissolved oxygen, essential for most marine life, becomes scarce but doesn't disappear entirely as once believed. Recent measurements by the 5 Deeps expedition revealed oxygen concentrations at the bottom of the Challenger Deep to be approximately 20% of surface values, low but sufficient to support specialized aerobic life. This discovery contradicted earlier assumptions that the deepest ocean would be almost entirely anoxic, demonstrating how our understanding of trench chemistry continues to evolve with improved measurement techniques. Perhaps the most significant chemical features of the trench are the specialized microenvironments created where geology meets biology. Along the trench's western slope, scientists have discovered numerous serpentinization-driven hydrothermal systems, locations where seawater reacts with exposed mantle rock from Earth's interior. These reactions produce hydrogen, methane, and a variety of other reduced compounds that serve as energy sources for chemosynthetic microorganisms. The Shinkai Seep Field, located at approximately 5,800 meters depth on the inner slope of the trench, exemplifies these chemical oases. Here, fluids enriched with hydrogen sulfide, methane, and other compounds support dense communities of specialized bacteria that oxidize these chemicals to obtain energy, a process called chemosynthesis. These bacteria form the base of unique food webs that function entirely independently from the photosynthesis-based ecosystems familiar to us on Earth's surface. Acidity levels in the trench present another chemical dimension of interest. While surface oceans have experienced acidification due to absorption of atmospheric carbon dioxide, the trench environment shows different patterns. At extreme depths, the pH actually increases slightly compared to mid-depth waters, creating a more alkaline environment. This pH gradient influences everything from carbonate shell formation to the functioning of cellular proteins in trench organisms. The trench also serves as a sink for anthropogenic compounds that have entered the marine environment. Recent expeditions have detected persistent organic pollutants, microplastics, and even radioactive carbon-14 from nuclear weapons testing in organisms and sediments from the deepest parts of the trench. These discoveries demonstrate how human activities affect even Earth's most remote environments and raise important questions about the long-term consequences of these contaminants in deep-sea ecosystems. Notably, the extreme pressure in the trench affects carbon cycling in unexpected ways. Under Hadal conditions, certain organic compounds resist breakdown more effectively than at lesser depths, potentially making the deep trenches significant reservoirs in the global carbon cycle. This finding has implications for understanding Earth's climate systems and how carbon moves between the atmosphere, surface ocean, and deep marine environments. These complex chemical conditions, combined with extreme pressure and near-freezing temperatures, create powerful selective forces driving the evolution of trench organisms. By studying how life adapts to and even exploits these challenging chemical environments, scientists gain insights not only into the limits of terrestrial biology, but also into how life might exist in analogous high-pressure environments elsewhere, in the solar system, such as beneath the ice shells of Europa or Enceladus. Exploring the Mariana Trench represents one of the greatest engineering challenges humans have ever confronted. The extreme conditions of the Hadal environment, particularly the crushing hydrostatic pressure, have necessitated technological innovations that push the boundaries of materials, science, energy storage, and systems engineering. The story of deep-sea exploration is as much about overcoming these technical barriers as it is about scientific discovery. The most fundamental challenge is constructing vessels capable of withstanding pressures that would collapse conventional submarines like eggshells. At the bottom of the Challenger Deep, every square centimeter experiences force equivalent to the weight of approximately 1,100 kilograms. To survive these conditions, modern Hadal submersibles typically employ pressure hulls made from specially formulated titanium alloys or glass-ceramic composites shaped as perfect spheres, the geometric form best able to distribute pressure evenly. The bathyscaphe Trieste, which first reached the Challenger Deep in 1960, utilized a different approach. Its pressure sphere was constructed from forged steel with walls 12 centimeters thick and contained a small passenger cabin just 2 meters in diameter. The vessel's buoyancy came from a large float filled with gasoline, which, being less compressible than water, maintained positive buoyancy even at extreme depths. This innovative but cumbersome design limited maneuverability and scientific capability. Modern deep-diving vehicles like James Cameron's Deep-Sea Challenger and the Chinese Fenduzi submersible represent quantum leaps in Hadal engineering. These Vessels employ sophisticated syntactic foam, epoxy resin filled with hollow glass microspheres, for buoyancy, reducing weight while maintaining structural integrity under pressure. Their titanium pressure spheres incorporate precision machined joints and viewports made from specially formulated transparent ceramics that can withstand pressures exceeding 1,000 atmospheres. Power systems present another critical challenge. Traditional underwater vehicles use batteries that must supply all energy needs during a dive, as combustion engines cannot operate without oxygen. The latest generation of Hadal vehicles employs lithium-ion or lithium polymer battery systems, specifically engineered to function efficiently at near-freezing temperatures and to pack maximum energy into minimal space. These power systems must simultaneously run propulsion, life support, scientific instruments, and powerful lighting arrays necessary to illuminate the perpetually dark environment. Communication with surface vessels represents yet another technical hurdle. Radio waves cannot penetrate seawater effectively, forcing deep-diving vehicles to rely on acoustic signals that travel as sound waves through water. These systems offer extremely limited bandwidth, often just a few bits per second, necessitating autonomous operation during much of a dive. Modern Hadal vehicles increasingly incorporate sophisticated artificial intelligence systems that can make operational decisions without human input when communication with the surface is impossible. Scientific instruments deployed in the trench must also be specially engineered to withstand extreme conditions. Conventional electronic components often fail under high pressure as microscopic air pockets collapse. Engineers overcome this by pressure-compensating equipment, flooding it with incompressible silicone oil, or designing completely solid-state systems without air gaps. Even something as simple as a water sample collector becomes a sophisticated device when it must maintain sample integrity while transitioning through almost 11 kilometers of pressure change. Unmanned systems have increasingly expanded our access to Hadal environments. Autonomous underwater vehicles like the hybrid, remotely operated vehicle Nereus, which unfortunately imploded during a 2014 mission in the Kermadec Trench, and various Hadal landers have allowed for longer duration observations and sampling than is possible with human-occupied vehicles. These robotic explorers can operate for days or weeks, collecting data and samples before returning to the surface. Despite these technological advances, the Mariana Trench remains more inaccessible to humans than the surface of the Moon. The engineering challenges of operating in this extreme environment continue to drive innovation in materials science, energy storage, and autonomous systems, advancements that often find applications well beyond ocean exploration. In the perpetual darkness of the Mariana Trench, nearly 11 kilometers below the ocean's surface, exists a biological community that defies conventional expectations. Here, beyond the reach of sunlight, traditional ecosystems built upon photosynthesis cannot exist, yet life thrives through alternative pathways that have only recently begun to reveal their complexity to scientific investigation. The foundation of this Hadal food web differs fundamentally from the photosynthesis-based systems familiar to us on Earth's surface. Without light, primary production, the creation of organic compounds that sustains all higher life forms, must occur through chemosynthesis. Specialized bacteria and archaea harness energy from chemical reactions, particularly the oxidation of methane and hydrogen sulfide released through geological processes in the trench. These microorganisms serve as the base producers in a food chain that extends to include complex multicellular organisms. One critical energy input comes through what marine biologists call marine snow, the continuous shower of organic detritus that drifts down from the productive surface waters. This material, composed of dead plankton, fecal pellets, mucus webs, and other biological remnants, undergoes extensive processing during its multi-week journey through the water column. By the time it reaches trench depths, only about 1% of the original organic matter remains, consisting primarily of the most recalcitrant compounds. The scarcity of this food source has driven remarkable adaptations among trench scavengers. Amphipods, resembling pale, oversized sand fleas, have developed highly efficient digestive enzymes capable of breaking down virtually any organic material they encounter. Some species, like Hirondelia gigas, produce special cellulases that can digest wood fragments that sink to the trench floor, materials that most marine organisms cannot utilize. When rare bonanzas like whalefalls, the sunken carcasses of large marine mammals, reach the trench floor, these scavengers appear in staggering numbers within hours, demonstrating how efficiently Hadal organisms detect and respond to food opportunities. The role of pressure in shaping this food web cannot be overstated. The enormous hydrostatic pressure at trench depths influences every aspect of biological function, from biochemical reactions to physical structures. Species found in the trench cannot typically survive at shallower depths, while surface-dwelling organisms would be instantly crushed if transported to the Hadal zone. This pressure barrier creates an isolated ecosystem that has evolved independently for millions of years. Predatory relationships in this environment remain poorly understood but appear to function differently than in shallower waters. While the Hadal snailfish, Pseudoliparis swirei, represents one of the top predators in this system, the scarcity of large, active hunters suggests that the harsh conditions of the trench may favor scavenging and deposit-feeding strategies over active predation. The energy expenditure required to chase prey may simply be too costly in an environment where conservation of energy is paramount for survival. Perhaps most mysterious are the microbial communities within trench sediments. Recent research has revealed unexpectedly high microbial cell counts in the deepest parts of the trench, in some cases higher than in shallower ocean sediments. These communities appear to include numerous novel lineages of bacteria and archaea, with unique metabolic capabilities adapted to high-pressure environments. The full diversity and ecological roles of these microorganisms remain largely unexplored, representing one of the most significant knowledge gaps in marine microbiology. Viral ecology represents another frontier in our understanding of trench biology. Preliminary studies suggest that viruses may play crucial roles in nutrient cycling and genetic exchange within Hadal environments, potentially serving as agents of evolutionary innovation in these extreme conditions. The pressure-resistant structures and infection mechanisms of these Hadal viruses remain almost entirely unstudied. The Hadal food web's isolation and extreme conditions have created a natural laboratory for understanding life's adaptability and the minimum requirements for complex ecosystems. As climate change and human activities increasingly impact ocean systems, determining the resilience of these deep-sea communities becomes increasingly urgent for conservation efforts and our broader understanding of Earth's biological diversity. As we stand at the threshold of a new era in deep-sea exploration, the Mariana Trench represents not just a geographical extreme, but a scientific frontier whose investigation may reshape our understanding of Earth and life itself. The coming decades promise unprecedented insights into this mysterious realm as technological innovations overcome the barriers that have historically limited human access to the deepest ocean. The future of Hadal exploration will likely be defined by longer duration missions and more sophisticated autonomous systems. While manned submersibles have captured public imagination, the practical limitations of human presence at extreme depths, including life support requirements and the psychological challenges of confinement in a small pressure sphere, have restricted dive times to mere hours. Next-generation autonomous underwater vehicles, AUVs, and hybrid systems will enable missions lasting weeks or even months, allowing for comprehensive mapping and continuous monitoring of trench environments. The Chinese research vessel, Tansuo-1, has already deployed Haidu, an autonomous robotic system capable of reaching full ocean depth and operating for extended periods. Similar systems under development in Japan, the United States, and Europe promise to create an international network of Hadal exploration capabilities. These robotic explorers will likely incorporate advanced artificial intelligence systems, allowing them to recognize and investigate unusual features or biological phenomena without human direction. Critical capabilities when communication with the surface remains severely limited by the physics of acoustic transmission through water. Sampling technologies represent another frontier poised for breakthrough. Current methods often damage or alter pressure-sensitive organisms during collection, limiting our understanding of their natural state. Next-generation pressure-retaining samplers will maintain specimens at in situ pressure throughout the collection and analysis process, revolutionizing our understanding of hadal biology by allowing observation of organisms in their natural pressure environment, rather than in the artificially decompressed state in which we've typically studied them. These technological advances will enable scientific investigations addressing fundamental questions about the trench environment. Ongoing research aims to understand how hadal organisms repair DNA damage from naturally occurring radiation, knowledge that could have applications in cancer treatment and radiation protection for astronauts. Other studies focus on pressure-adapted enzymes that function efficiently in extreme conditions, potentially yielding new catalysts for industrial processes that could operate at lower temperatures and energy inputs than current methods. The Mariana Trench may also provide insights into questions about the origins of life on Earth. Some origin of life theories suggest that high-pressure environments near hydrothermal systems might have provided conditions favorable for the earliest biochemical reactions. By studying modern analogues in the trench, researchers hope to test hypotheses about life's beginnings that remain difficult to examine in laboratory settings. Beyond Earth-focused science, trench research has implications for astrobiology, the search for life beyond our planet. The pressure conditions in the Challenger Deep approximate those thought to exist in subsurface oceans on Europa or Enceladus, moons of Jupiter and Saturn respectively. Understanding how Earth life adapts to these extreme pressure environments provides valuable reference points for considering what forms extraterrestrial life might take in similar conditions elsewhere in our solar system. Conservation concerns increasingly influence the future of trench exploration. Recent discoveries of microplastics and persistent organic pollutants in trench sediments and organisms demonstrate that even Earth's most remote environments are not immune to human impacts. Establishing baseline measurements and monitoring programs for these contaminants has become an urgent priority before potential commercial activities, including deep-sea mining in adjacent regions, further impact these pristine ecosystems. We continue our journey into Earth's deepest waters. The Mariana Trench stands as a testament to both the limits of our knowledge and the boundless potential for discovery. In this extreme frontier, where darkness, cold, and crushing pressure create conditions once thought incompatible with life, we find not only remarkable adaptations, but also humbling reminders of how much of our own planet remains unexplored, unknown, and unimagined. In the vast expanse of our planet, where unexplored territories seem increasingly rare, one frontier remains stunningly alien and largely uncharted. Not in space, but nearly 11,000 meters beneath the Pacific Ocean's surface lies the Mariana Trench, Earth's deepest known point and perhaps its most enigmatic environment. This abyssal realm, stretching like a crescent-shaped scar for 2,500 kilometers along the ocean floor, represents one of humanity's last great terrestrial unknowns. The story of the Mariana Trench begins over 180 million years ago, when the massive Pacific tectonic plate began its slow, inevitable collision with the smaller Philippine plate. As the heavier Pacific plate slid beneath its neighbor, in a process geologists call subduction, it carved out what would become the deepest oceanic trench on our planet. Today, this underwater canyon reaches depths that would swallow Mount Everest, with more than 2,000 meters to spare. At the trench's nadir, a small valley-like depression called the Challenger Deep, the ocean reaches a staggering depth of 10,934 meters. Here, water pressure exceeds 1,100 atmospheres, equivalent to having 50 jumbo jets balanced on your shoulders. The temperature hovers just above freezing, while perpetual darkness has reigned for eons, broken only by the bioluminescent glow of strange creatures, and in recent decades the artificial lights of human explorers. These extraordinary conditions have created what scientists consider one of the most extreme environments on Earth. Yet remarkably, life persists here. The discovery of thriving ecosystems in the lightless depths has revolutionized our understanding of life's resilience and adaptability, challenging long-held assumptions about the conditions necessary for biological processes. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Human exploration of the trench remains extraordinarily rare. The crushing pressure at these depths requires specialized equipment that few organizations possess. When Swiss oceanographer Jacques Piccard and U.S. Navy Lieutenant Don Walsh first reached the Challenger Deep in 1960 in the bathyscaphe Trieste, they became pioneers in a more exclusive club than even astronauts, fewer humans have, traveled to the deepest part of our oceans than have walked on the moon. In 2012, film director and explorer James Cameron completed the first solo descent to the Challenger Deep in the Deep-Sea Challenger submersible. His historic dive lasted 7 hours, with about 3 hours spent on the seafloor collecting samples and capturing high-definition footage of this alien landscape. Since then, only a handful of other manned expeditions have reached these extreme depths, including ventures by explorer Victor Vescovo in the DSV Limiting Factor submersible. These pioneering expeditions have provided invaluable glimpses into an environment that remains largely mysterious. As we prepare to journey deeper into our exploration of the Mariana Trench, we stand on the threshold of discovery, peering into an abyss that promises to reshape our understanding of our planet and the remarkable adaptability of life itself.